These are the lesson activities for 5.3. Consider the matrix A, 1, 3, 4, 2. Diagonalize the matrix if possible. That means find D and P such that A equals PD, P inverse. So D, that's made up of eigenvalues. And P, that's made up of eigenvectors. Okay, so I need to find the eigenvalues and eigenvectors. So to find the eigenvalues of a matrix, we calculate the determinant of A minus lambda I and set it equal to 0. So that would be the determinant of 1 minus lambda, 3, 4, 2 minus lambda. The determinant of a 2 by 2 is just AD minus BC. We set that equal to 0. Multiply this out and I get 2 minus lambda minus 2 lambda is minus 3 lambda plus lambda squared minus 12. Okay, combine like terms. 2 minus 12 is negative 10. Factor. And we get lambda equals 5 and negative 2. So once I have the lambda values, I can make my D. My diagonal matrix is lambda 1, 0, 0, lambda 2. So you just put the eigenvalues on the diagonal. So I'm going to have 5, 0, 0, negative 2. And it doesn't matter if you put the 5 here or here. They can swap. If you swap them, then your P is just going to swap the columns as well. Okay, so I used up way too much space here. Now I need to try to find an eigenvector that corresponds to each eigenvalue to make up P. So for lambda equals 5, I need to solve, I need one vector that satisfies AX equals 5X. So I need one vector, 1, 4, 3, 2 times XY equals 5 times XY. So this is the definition of eigenvalue, eigenvector. So let's see, if I multiply this out, I get x plus 3y equals 5x, and 4x plus 2y equals 5y. So let's see, I'll solve for y. I get 3y equals 4x, so y is 4/3 x. And this one, I get 4x equals 3y, so y equals 4/3 x. Again, it's very common. You either get two of the same equation, or one equation gives you like 0 equals 0 or something like that. So a vector that corresponds to lambda equals 5 would be any xy that satisfies this equation. So I think I will choose x to be 3. And then when I put a 3 in for x right here and get y, that means y would be 4. So that's one of my eigenvectors. Okay, and then the other one, lambda equals negative 2. I need to solve ax equals 2x. So 1, 4, 3, 2 times xy equals negative 2 times xy. So I get x plus 3y equals negative 2x. So 3y equals negative 3x. So y equals negative x. So a vector, an xy pair that satisfies this equation would be 1, negative 1. But any vector will do. You don't have to pick the same ones I did. I try to avoid fractions, which is why I picked 3, 4, but you definitely could have put a 1 in for x and gotten 4/3 for y. And here I put a 1 in for x and got -1 for y. Any vector that satisfies your equations will work. So my P is a matrix where the columns are the eigenvectors that correspond to the eigenvalues in D. So in D, I put the 5 in the first column. So in P, I'm going to put the eigenvector that corresponds to 5 in the first column. So 3, 4. And then in D, I put the -2 in the second column. So I need the eigenvector that corresponds to the -2 in the second column of P. So there's my D, and there's my P. I'm not going to ask you to find P inverse, just the D and the P. Okay, show that the matrix equation that defines diagonalizable, this equation, is equivalent to AP equals PD. Okay, so if A equals PD P inverse, I'm just going to multiply both sides of this equation on the right by P. So multiply this side on the right by P, and multiply this side on the right by P. So I get AP equals P inverse times P. Those become the identity, and it just goes away. AP equals PD. Check. All right, so now I'm going to verify my diagonalization from number 1 by showing that AP equals PD. Okay, so A was 1, 4, 3, 2. And P that I calculated just a minute ago is 3, 4, 1, -1. And I want to show that is equal to P times D. So P is 3, 4, 1, -1, and D is 5, 0, 0, -2. So if these two multiplications give me the same result, I will have verified that I found a correct P and D. And this is helpful because like the answers that I give in the back won't always look like yours, because you could have swapped the columns of D, you could have used different eigenvectors to put into P, but this is a way you can always check. All right, so if I multiply this, I get 3 plus 12 is 15. That was first row times first column. First row, second column is 1 minus 3 is -2. And then 4 times 3 plus 2 times 4, so that's 12 plus 8 is 20. And 4 minus 2 is 2. Okay, same thing down here. Multiply these two matrices, so I get 15 plus 0. 3 minus 2, 3 times 0 minus 2. And then 4 times 5 minus 1 times 0 is 20. And 4 times 0 plus -1 times -2 is 2. Okay, these are equal. Check. I diagonalized correctly. -1, yeah. Express a to the 8th, A from question number 1, as a product of 3 matrices. Okay, so a to the 8th, because it's diagonalizable, you can write this as P d to the 8th times P inverse. And I don't think I'm going to write this all out. D to the 8th is really easy. So let's see, what was P? P was 3, 4, 1, -1. Right? Okay, and then D to the 8th, the way you raise a diagonal matrix to a power is that you can just raise each entry to the power. So this would be 5 to the 8th, -2 to the 8th, 0, 0. And then P inverse, which I'm not going to bother finding, but this is the 3 matrices that you would multiply together to get a to the 8th.